Yes, so here we are going to enter in the next section basically, that is magnetism and electromagnetism, and I believe that uh, it is one of the hard topic for the students, but the beauty of this topic is that there are no calculations at all. Most of the calculations you have done in your current and electricity, and the only calculations which are here, they are in your transformer. Okay, rest there are very few calculations. Yeah, no calculations, not few, no calculations at all. Okay, so magnetism and electromagnetism, it here I have divided this into three parts. One is your magnetism, second one is your electromagnetic forces, and third one is your magnetic induction. So basically this is the yani division of this. So first I'm talking about magnetism. So when we talk about magnetism, I believe that no need to read these slides by all means, but the important points I have made bold, and what is necessary for your basic knowledge, and what is necessary for your basic concepts. Everything is mentioned here, but where I will emphasize for the paper, you have to be careful about that. Rest some informations are not for the paper, they are just for your concept and information. I mean, just like information, so take them as an information, but not so seriously, right? Okay, so basically when we talk about magnetism, it is the natural property of some materials which due to which they attract and repel the materials of the materials occupying the same properties, or materials having the same properties. Like, if I have a magnet, then the magnet will attract another magnet or repel other magnet. But if I have a magnet, it will either attract, sorry, it will attract the iron material, like, which is which is a magnetic material. So we can simply say that these all are the properties by which we can make it uh, in detail. So there are some materials like steel, cobalt, nickel, and iron. They have the magnetic properties. So magnet is a sort of material which consists of the atom. So here I have shown you this diagram. In this diagram, I tried my best to represent the atom at its yani the magnet at its atomic level. This is actually the magnet. This is the magnet what I have shown to you, yani inside and outside. This is its north pole. This one is your north pole, and the other side is your south pole. So you can simply say that north pole is that pole in which all the magnetic domains align themselves towards north, and other one is definitely south. So inside the atom, there is the spin of the atoms, and due to that spin, they align themselves in a specific direction. So these materials in which this all happens, they are called your magnetic materials, what I have enlisted in the above. Okay, so this is the explanatory slide of these all what I have shown you, right? That charged particles are electrons, they have the spin, and they actually align themselves in a specific direction that makes the poles, and then these are called your magnetic domains. What do we call them? These are your magnetic domains inside. So those materials in which the magnetic domains are able to align, they are called magnetic materials or magnetizable materials. And those in which they cannot be magnetized, they are called non-magnetic materials, right? So domains are aligned in such a way that uh, yani, here there is very important thing. For example, in this material, if you see this material, all the domains are not aligned in one direction. There are few like this. It is not aligned in the direction of the other ones. This is that. So you can hunt the odd ones out, but overall the majority of all these atoms, they have the like spin. I mean, they have aligned themselves in a fixed direction. That is why this is considered as north, and the other one is at the south. So I told you that domains are aligned towards North Pole. So where the domains are aligned, that arrowhead is named as North Pole. So once they all are aligned, once they all are aligned, we get a strong magnetic field on the edges of that material, which are called, actually it's poles. I will talk about those poles. That poles are those areas where the magnetic field is strongest. Okay, this is one, yani it is not mandatory for you to know about the name of lodestone, but it is that uh, word which led us to know about the magnetic properties of the material in detail, because that magnetic material, or this was used to lead the people through the journey, like the magnetic compass. You people know about that, it's very interesting है. मैं इसके ऊपर आप लोगों को ज्यादा डिटेल्स बताऊं. Magnetic compass is being used to have a direction, but it was the old history in which the stones were just pivoted, and they were moved to, or they were made to rotate at a specific direction. They were pointed towards a specific direction. That's why they were giving you a direction. That is the compass, magnetic compass needle. And yes, in magnetic compass, just see that one side which is usually painted red or blue or whatever, that is yani its north pole. This is the north of this magnetic compass, and this is its south. So south and north, definitely you people know that they point in such a way that north is attracted by the south and south is attracted by the north. So when you bring a magnet closer to it, what happens? Its magnets south is pointed towards the north of the magnet, of that permanent magnet. Compass south is pointed towards north of the permanent magnet, and likewise, if you say that its north will be pointed on the other side. So in this way, you can say that this is the game of the magnetic compass. I will talk about that. Then I was talking to you that I will discuss about the poles. So when we talk about the properties of the properties of magnet, so these all, if you see, it's a good high resolution picture. So these all are the iron fillings, and when you put some iron fillings, or when you put a magnet in the iron fillings are likely to be attached on the ends of the bar magnet. That is why these are called poles. So here, the iron fillings are just attracted, or they are attached uh, in between north and south pole. Here, do you see? This is the north and south pole. So the strongest gathering is here in between north and south. But if you place two north and north in front of each other, or south and south, so there will be no field here. That is why the feelings are not attracted here. So that tells us that uh, in the opposite poles there is an attraction between, and in like poles there is a repulsion between. So magnetic fields have been repelled here, if you see. Got it? So here is the plan diagram, that like poles repel and unlike poles attract. This is the law of magnetism. I believe that these all are very basic things for you. So here I have divided, or I have enlisted some of the magnetic and non-magnetic materials. So this is the slide which will tell you about that iron is a magnetic material, steel is a magnetic material, nickel is a magnetic material, right? And non-magnetic material, gold is non-magnetic, copper is non-magnetic, aluminum is non-magnetic. Okay, so we can have this general knowledge. And one more important thing, that if you break a magnet into its in I mean when you break a magnet into very small pieces, what will you have, or what will be the behavior of the pieces? that they will make the magnets. Yani, let's say this is an unbroken magnetic bar. So here it is converted into two pieces. So you have two perfect magnets, yani complete magnets. Here it is broken into four. So you have four magnets. So whatever the small piece you make from a magnet, it will be a magnet. It will not be a pole. For example, mean if you just broke it into two pieces, you must be thinking, okay, yaar, right wala it will be north pole and south wala it would be south pole. No, it is not like that. Every single piece of the magnet will be a entire magnet, yani a complete magnet. So if this is south pole, then this side would become north, and if this is north, this side would become south. So you have to keep these points in your mind. Then this is basically repulsion is a test of the magnetism. Yani if you keep a if you keep a iron piece or magnetic material and you just believe कि, okay sir this is magnet, so this is not the test, because attraction is possible um, in iron, steel, as well as any other magnet when it is placed with unlike poles. But repulsion will only take place when there is a magnet which has like poles. So like poles तो आपको पता है, like poles can take place only in the magnets, nothing else. है ना? So remember this thing, that these are the opposite poles. So attraction is taking place, repulsion is there in like poles. So this is the magnetic material. It does not have any pole. So when it is brought closer to north, it is attracted. When it is brought closer to south, it is attracted. And this is really important slide for you. Remember this thing. Okay?
Yes, sir, got it.
Got it, sir.
Because there are so many questions which are coming from this point, that okay, this material is iron, iron rod is brought closer to north, it would be attracted. What will happen to the iron rod when it is brought closer to south, etc., etc.? So you have to keep all these points in your mind. So I have talked about the magnetic materials in detail. So here we go to the earth's magnetic field, right? Earth's magnetic field. So earth is basically a complete magnet. I mean, if I say that Earth is just like a bar magnet, because of the molten magma or molten metals inside, the Earth behaves like a magnet, and it has a magnetic field. It has a magnetic field inside it. And when it has a magnetic, sorry, not inside it, around it. And when we see the magnetic field, remember one thing, these labelings are very important. This is the north magnetic pole. What is that? This is the north magnetic pole. Okay. And this is the south magnetic pole. Got it?
Yes,
Okay.
sir.
On the other diagram, if you see that if we place a, or if we consider the earth as a bar magnet, like the just the diagrams, arrows, yani diagram has a little bit different in graphics. The problem is this north pole of the magnetic field is considered to be the geographic north pole. Okay, there is a problem in this diagram. There is a problem in this diagram.
Is it opposite?
Actually, yes, it is opposite. This is not the. This is basically your magnetic north, geometric north. This upper pole is your geometric north pole. Mean that pole which is obtained uh, by the magnetic compass. But this pole is actually your magnetic south pole.
But, sir, when
Okay,
the magnet
this
is
is
pointing, when the north side of the,
This is magnetic south of Earth. Yes, what are you saying? Yes, Mariam. Do you have any suggestion or any question? It is your magnetic south. If it would not be magnetic south, the north of the magnet will never be pointing itself towards it. Remember one thing, right? And this is your magnetic north. This is your magnetic north, and that magnetic north is basically why, because when you keep a magnet on the earth, its south is pointing downwards. That means that is why upper pole is called north pole. What do we call it, or why do we call it north pole? Because when we place a magnetic compass, it points towards it, its north is pointed towards it. That is why north pole, and this is your south pole. Do you get it?
Sir, but
So
like,
this
why
is
is it the
basically,
opposite?
yeah,
You're saying that the one on the bottom, it is the magnetic North Pole, and the one on the top,
no,
it is the magnetic South Pole?
yes, you're right.
So, but like, isn't the magnet pointing the magnet's North Pole pointing upwards? So the thing upwards, it should be the magnetic north and not the magnetic south.
Okay, मैं तुम्हें दिखाता हूँ एक मिनट.
Or are you
If
talking about
this
it
is,
in terms of attraction?
yes, definitely, this is, let's say, Earth, and here is its own magnetic field, right? And if we talk about its own magnetic field, we simply say that this is south of Earth magnet, and this is north of Earth's magnetic field. Are you getting my point? That Earth's magnetic field, this is basically the Earth, and it has the lower side as north and the upper side as south. But when you place a magnetic compass at the top of it, just you will hover it, then what will happen? What will happen? Let's say, do you see my diagram?
Yes, sir.
Okay, that side, which is basically the circular one, in which there is a circular rounding, I mean the rotation arrow. Let's say that is your north. Okay, let me make it. Maybe I would be able to make it. Otherwise, no. Let's say this is north and this is south. So, what do you think? When I will when I will uh, place it, place this magnet over here, what will happen to its north? Will it be stable? Its north will be pointing in this way, and south will be pointing on the other ways. Enough?
Yes, sir.
Okay, so let me erase this for you. So it means that the magnetic north will be pointing, I mean, north of the magnet which you are placing on the earth, its north will be pointing this way, and south will be pointing this way. Is it?
Yeah.
So that means that when you are having a magnetic compass will show you that north is pointing upward. So that is why we call that this north pole. But it is not actually the north pole. This is your this
Magnetic
is the
South
pole.
Pole. No, North
Yes,
Pole.
this is magnetic south, right? This is your geometric north, but magnetic south.
Oh, okay. Got it.
Yes. Yes, Ariba.
Yes,
Ariba, are
sir.
you there?
Sorry for the late reply on my mic.
Okay, so is this clear? I mean, any confusion in that?
No confusion.
Okay. Is Khadija in the class?
No, sir. It's you, me, and Mariam.
Okay. So it is geometric south, where it is your magnetic north. Remember this thing. This is basically the game of Earth's magnetic field. Okay. So after this all, when we talk about the induced magnetism, it is not basically the induced electromagnetic induction. It is just induced magnetism. So induced magnetism is a is a study of the situation when you are going to make something magnetized, or temporarily it behaves magnetized. Okay. Hello. Do you people hear me? Hello. Hello. Do you hear me? Is there any voice problem with my mic? Mariam, Ariba, do you hear me? Hello. Do you people hear me? Am I audible to you? Okay, so I was talking about that induced magnetism and electrical methods of magnetization. That is in your syllabus. So, induced magnetism is basically the temporary magnetization of any material. When you bring it in the magnetic field, it is behaving like a magnet. So, that is basically the magnetic induction is a process to induce the magnetism in an ordinary piece of magnetic material. In induced magnetism, that is a temporary process. It means when you will keep that magnet in the magnetic field, it will behave like the magnet, but when you will remove it, it would not be a magnetic behavior, or it would not have a magnetic behavior. So that is why that method involves simply placing a magnetic material in a close or in a strong magnetic field without touching it, right? Then what happens? The ends, nearer ends, they get opposite polarity on the magnets. So for example, soft iron bar is attracted and attached to the permanent magnet, and the magnetic induction process reveals how the magnetic material be attracted. Yani, when you will keep the magnet, for example, here is a magnetic material, and that magnetic material is having yani you keep it, or when you brought it closer to north pole, what will happen? What will happen? That material will induce its unlike pole, where to the to the nearby pole, to the nearby pole. For example, it is the north pole, and that magnetic material which is brought closer, it will induce a south pole here, and it would be attracted. But when it is brought closer to south, it would induce a north on the nearby side, and it will be attracted. So just remember one thing, that magnetic material is always attracted, nothing else. Magnetic material is always attracted, not magnet. Okay, ji? Is it clear to all?
Yes, sir.
So just getting into detail of that, that methods of magnetization are several methods of magnetization. Let's say if you see that the methods are Stoke method, although that method is not asked in detail, but we have to go through that. That in Stoke method, we just place a piece of magnetic material, right, and we just rub a material or magnet on it. For example, here is that. I can show you on that one. So you are just stroking it. There is a steel bar. This is not a magnet, Miani. This is not yet. It is not a magnet. But when you stroke it, stroking the magnet with another magnet, just rub it and drag it outside. Rub it and drag it outside. So that this north would basically carry all the souths along with it. So due to that, you know what will happen? This side would become south and this side would become north. So simply speaking, in stroking the pole from where you are leaving, that would get the opposite pole by which it is being stroked.
So you mean if you're rubbing the North Pole over the bar, so the bar gets
Yes.
the South Pole?
No, no, no. Not bar will not get north south pole. Actually, the end from where you are leaving, it will get south, and end at which sorry, the end at which you are entering, that will get. So just let me write. Sorry, just a second. Let me select the
Like,
color.
how are they divided?
Just a second. I will explain you. Actually, what does this north do? North attracts all south pole domains towards it. Na, are you getting? Just see this diagram. What is that north doing? Mhm.
Attracting the South.
Yes, attracting the south of those all small magnets. Okay. So due to that, what happens? The pole which is being rubbed, this is pole. Remember this thing. There is a difference between pole and end. Please mind it. This is pole, okay, and this is end, okay. So this end would become south, and this end will become north. This is end, and this is pole. So just make this
So,
clear. Mm-hmm.
how do you
You have a
differentiate
question?
between a pole and an end?
Oh yeah, end is the basically a side of any non-magnetic material,
Uh huh. So the thing, so
and
the
pole
side where
can
you're
be either
rubbing it
north or
on,
south.
that will be the pole.
Yes, this is I'm sure that this is a magnet who has south here and north here. Got it?
Okay, you got it, got it.
And this thing which is steel bar, this is not magnetized yet. So I cannot say that it has poles until unless it is stroked and it becomes magnetized. So here in diagram number 2, the bar is
The
magnetized. Do you
perovskite.
see? Is it clear?
Yes, sir.
Okay. So when you stroke by two ways, this makes strong magnets actually. And the reason is, yani, the method is same. If you are stroking with north, the end from where you are leaving that stroking, that would cause south. And if you are stroking with south, in this way, yani in this method, one end is stroked by north and the other end is stroked by south, so that you can create like poles. If you will stroke it with like poles, यानी वो दोनों साइड पे आप नॉर्थ नॉर्थ से स्ट्रोक कर रही हो, तो it would never be a magnet. ये जो स्टील बार है ना, it will never be magnetized. Is there anyone else, or you and me are the only living organisms here in the class?
So Ariba isn't there in the class right now.
Okay, good. Okay, this is the method. This is basically magnetization with direct current. Really, really important point. When you want to magnetize a unmagnetic material, you have to use a direct current. Really important. So direct current means battery should be direct voltage battery, DC. Okay, so what happens? You have a long coil, and in that long coil, you have a yani practically it looks like this. You have a long coil, and in that long coil, you just apply a voltage here, right? And those voltages are increased. Yani dekho, it is this consists of AC and DC both. But what you need the DC part of this DC. So you will connect the voltages with DC, you will increase the voltages, and when you will increase the voltages, you will just slowly drag the rod out. This is basically the rod, which is steel bar, you can say, because I'm going to magnetize that. So it would be dragged out, and by dragging it out, that end at which, yani the end which you are going to drag out, it would become north, and the other one would become south. For example, the procedures, the steps are there, and then I will let you know. This is very important to know that connect the solenoid to a DC power supply, place the steel bar inside the solenoid, switch on the DC, and increase the current and slowly drag the steel bar out. Okay. And when the current flows through the solenoid, a strong magnetic field is produced which magnetizes the steel bar, and the pole of the magnetized steel bar is determined by using right hand grip rule. So, as I told you, in right hand grip rule, I will explain it later on, don't worry. So, here there will be a south, and here there will be a north. So, in this way, your steel bar would have north and souths on that one. Okay. Here, the important note is the solenoid is made up of several hundred tons, because by making 2, 3, 4, 5 tons, it does not have any impact. So we make the solenoid hundreds of tons to enhance the magnetic field strength. So when we enhance the magnetic field strength, basically it retains the magnetic, yani it produces a strong impact on that what you are going to on the steel bar which you are going to produce, or which you are going to make a magnet. Okay.
Yes, sir.
Okay, अब आगे चलते हैं. The electric method is most effective method of magnetization and much quicker than that of, and it produces very strong magnets. So these all are the three specs you have to remember, that when we are going to have a magnetization, we use direct current, switch on the bar, drag it out slowly, and enhance the current level. Then there is a demagnetization method. Demagnetization method is basically the demagnetization method is when a magnet is there. Did you notice in the previous diagrams this subject was not a magnet, that was a steel bar, but now we are using a magnetic material. I mean magnet. So hammering, hitting, and dropping, they all cause the magnet to lose its magnetic properties. Yani, those domains would be misaligned, and when those domains would be misaligned, what will happen? Those The magnet would be no more magnet anymore. right? And yani, I have explained all of these on this slide, that why heating means it enhances the vibration of the magnetic domains, and this causes the magnet yani demagnetization, dropping again, and hammering and dropping are actually the same procedures. No, there is not a big deal. Then this is very important, the electrical method of demagnetization. For electrical method, I told you here deliberately that using an alternating current. What do we use? We use an alternating current, right? What alternating current is being used to produce yani to remove the magnetic properties from a magnet. Okay, so actually, what is the property of alternating current? Alternating current has a reversing polarity, and when it has a reversing polarity, it causes randomness in the magnetic domains. And when it has a randomness in the magnetic domains, just see, you put yani you placed a coil, and in that coil, what did you do? You just ye khatam karo. You just what did you do? You just put an alternating current, and when you put an alternating current, the steel bar is slowly dragged out of it, and magnetic field is then misaligned. That part which is dragged out, on that the magnetic field would be misaligned, and in this way it becomes non-magnetic. Okay, so you have to keep all these points in your mind. Just keep these 4 points, the procedure. Connect the solenoid of alternating current, place the magnet inside the solenoid, switch the AC, slowly withdraw or drag east-west direction. Usually it is east-west direction, and it is recommended to minimize the effect of Earth's magnetic field, and some distance away from the solenoid, and then you can switch off the current. That's it. So this is again more electric effective method of demagnetization. And magnetic field, and yes, then the next topic is magnetic field and magnetic field lines, right? Magnetic field and field lines. So you know that magnetic field is that region around a magnet where another magnet can experience a force, right? And that force is represented by field lines, and those field lines actually represent two things: strength and direction. So magnetic field strength is a vector quantity, so it has both magnitude and direction. This was an important information. So here are some sort of graphical representation of your magnetic field. So in the magnetic field, did you see, if the magnetic field line starts from the north of a bar magnet and they end up at the south, and if we have a horseshoe magnet, they would start from north and they would terminate on the south. Just see that. If I zoom it in, just look at this, right? They are starting from north and they are terminating at south. They have a beautiful aspect, that they would all be perpendicular to the surface, perpendicular to the surface, perpendicular to the surface. Wherever they are going to interact, they would be perpendicular to the surface. So if you have a coil, its one end would be north, from there the magnetic fields are generating, and the other end will be south, at which the magnetic fields are getting into the coil. So you will definitely be have this concept with you. Then unlike poles attract each other, because the magnetic field lines are directing from north to south, and they are just bringing these two poles closer. And like poles, they repel each other because the magnetic field lines are opposite in direction. That's why the repulsion takes place. So in like poles and unlike poles, you must know this thing. The important thing is, when the field lines are closer together, the points, they are called stronger points, or that is called, okay, the points are called strong points. Yani the field is called strong field. Okay,
Yes, sir.
and the points where the magnetic fields are apart from each other, you are separated out. they are called, or that area is called weak force. And magnetic field starts from north pole of the pole of any magnet and ends up at south pole of any magnet. Remember this thing. And inside the bar, or inside the solenoid, the magnetic field lines are from south to north. Just see that this is your north. I told you this is your north, this is your south. So magnetic field lines are from south to north inside the bar magnet. And in same goes here. Just see, inside definitely they have to they have to meet up at a point. So that is the point where they will join here. This
Sir,
yes.
how do you determine the direction of the arrows coming out of the North and South Pole?
Actually, with the iron fillings, we came to now, or with the help of the compass, magnetic compass. अभी आगे चल के इसी टॉपिक पे हम लोग डिस्कशन करेंगे इंशाल्लाह, बट टुमारो, नॉट टुडे. This is basically the direction of magnetic field lines inside the bar magnet. So we use the magnetic compass to find out the direction of the magnetic field lines. Here is the answer of your question. We place the magnetic compass near the poles of the magnet, and we just see where their arrows are pointing, and we just plot the points, right, in this way. And when we plot the points, the direction of the arrow is shown by, a direction of arrow shows the direction of north pole and south pole. Got it? For example, if you bring a magnetic compass, or if you place a magnetic compass closer to north, then its north would be pointing away. Are you getting it?
Yes, sir.
Okay. And in this way, this, yeah, you will just mark all the points here. This is north. Next north will be pointing on the other side, yani on the other point this way,
He's
here,
like,
here, here, and so on. So these all are the points which are pointing your north. So it means the magnetic field is pointing from north to south. That's it. Is it clear to you?
well, got it, sir.
So we will discuss this all inshallah in plotting the magnetic field lines. Yeah, this topic today in today's yani in sorry, in the next lesson. So I believe that it would be very clear to you.
Uh,
Okay.
yes, got it.
Okay. So any
Sir,
other question? Yes.
do you have the same notes, like the same notes for electricity?
Ah, yes. I'm trying to. Actually, I lost my data for these all years. What I have done. So I'm preparing that all again. It will take time. That's why I send you the electricity, current and electricity from the same folder. I mean, I can show you the folder from where I have just put it out.
That
But
is why when
I
I
could
was
not.
asking you for the notes of